Hello and welcome to this clip on pH curves and indicators. We'll cover the essential components of a pH curve, which is essentially a graphical plot of pH change when acid or base volume is altered when you add more acid or base during a titration. We'll look at why different acid-base combinations give different shaped pH curves, and how an indicator is essentially a weak acid that changes colour as the pH changes because it dissociates to different degrees. So if it changes colour, then obviously it can be used as a visual marker of neutralization taking place. And the clip will assume that you're already comfortable with the equilibria surrounding weak acids, as well as the fact that complete neutralization will mean that all the H+ ions and OH- ions in aqueous solution have reacted to form water. And it would be a good idea to make sure you're also familiar with the ionic product of water and the Kw expression, because the exam question we'll look at the end of this clip will assume that you're okay with those two ideas. This is essentially what a pH curve looks like. In this particular example, the base is being added to the acid. So at the beginning, as you'd probably expect, the pH value is very low. There's no base being added yet. As you add more base, the H+ ions start getting used up and the concentration of H+ decreases. This means that the pH will increase. So the equivalence point is when the quantities of H+ and OH- exactly match each other. The volume added at this point, in the case of this particular graph, the volume of base added at this point, has caused neutralization to occur. And pH changes rapidly at the equivalence point. In this particular case, you're adding base to acid, so the pH will rise rapidly at this particular equivalence point. After the equivalence point has been reached, if you keep adding your component, the pH will reflect that component. So in this particular example, it's the base that's in excess. So the equivalence point, or after the equivalence point, shows the point at which more base than acid exists in the mixture. It's also worth pointing out that the equivalence point is in the middle of that vertical line. So the equivalence point is the centre of the vertical section of the titration curve. And the part of the curve where the pH changes sharply is called the vertical section. The equivalence point sits within the vertical section. So as you'd expect as well, if you had the acid being added instead, it would form a similar shape but the mirror image. So obviously it's a good idea to watch out for this if you're given an example of a pH curve in a question. They'd expect you to be able to spot which component is being added to which by the shape of the curve. And just to quickly recap on the equivalence point in the vertical section, I've labelled them there for you so you can see how they can apply to the second curve, the second version, where the acid is added to the base. So let's have a quick look at what happens if we change the concentration. The graph is labelled showing that 0.1 mole per decimeter cubed, decimeter to the -3 base was added. If we double the concentration, what will happen is that the equivalence point will be reached at half the volume, in this case 12.5 centimeters cubed. If we were to halve the concentration, the equivalence wouldn't have actually been reached until 50 centimeters cubed. That would mean that the pH curve for a base of half the concentration would actually go off the graph. So what I've done is I've made the base 50% less concentrated. Therefore it takes 50% more volume to reach the equivalence point, which is why the equivalence for the red curve is taking place at 37.5 centimeters cubed. The pH curves that you're likely to come across in A-level will assume a 1:1 mole ratio of acid to base. So therefore it'll be monobasic acids that you'll be dealing with. But you may well be asked to predict the shape of a pH curve if the concentration of what's being added is changed by a significant amount. So it's important to bear this in mind too when looking at possible exam questions on this topic. And it's also important to have a look at the fact that the position and the range of the vertical section remains unchanged because it's the same acid-base combination being used. The positioning of the vertical section and its size, its range within the pH range, only alters if the type of acid and type of base that you're mixing together and titrating actually changes. So that's what we're going to look at next. So depending on the type of acid or base combination you use, you'll get different shapes. So you can see that they're quite markedly different from each other, even though they form the same kind of S shape. We're assuming that in these particular examples there's a base being added to an acid to keep it nice and simple. So let's go through each one in turn. If we look at the strong acid, strong base example, the vertical section is well defined and the equivalence point itself is close to pH 7. So when you're looking at a pH curve for a weak acid and a strong base, the vertical section is better defined at larger pH values but less so at smaller ones. The equivalence point is greater than pH 7. With a strong acid and weak base, it's the other way around. The vertical section is well defined at lower pH values but less defined at higher ones. The equivalence point is less than pH 7. And with a weak acid, weak base pH curve, the vertical section is poorly defined in all pH ranges. So the equivalence point exact pH value is very difficult to work out from this particular curve. An indicator is a weak acid which changes colour on dissociation. And that's because the weak acid itself will be one colour, and when it dissociates and the conjugate base is released, the conjugate base will have another colour. So in this particular instance, if OH- is added, it's going to react with the hydrogen ions and drive the position of the equilibrium to the right. So therefore the mixture will turn blue as the conjugate base is released. So if it's the opposite and you're adding acid in the form of H+, as the conjugate base reacts with the H+, HA is produced. Or I should really say the indicator as a weak acid is produced, H in, which turns the mixture red. So in this way an indicator can tell you the pH of your mixture. And different indicators work best within different pH ranges, so you need to choose your indicator carefully. So it's important also just to mention that during the shift in equilibrium from one side to the other, there'll be an intermediate colour seen. That intermediate colour is called the endpoint, or the point at which that colour is reached is called the endpoint of the indicator. And what this means in terms of the equilibrium is the concentrations of HIN and IN-, in other words the concentrations of the weak acid indicator and its conjugate base will be the same as each other. So the indicator that you choose should have a working pH range that matches the equivalence point of your titration. So now would be a good time to try a bit of thinking here. If you pause the video, see if you can decide which indicator is best for each of those three titrations. The first one should have a best choice of bromothymol blue, because the working pH range of bromothymol blue is from 6 to 7.5, as you can see. And the middle part of the equivalence point matches that value. In the second one, it's a bit difficult, isn't it? Because the middle of the equivalence point could be either methyl orange or bromothymol blue. Perhaps bromothymol blue is the best one here as well. It's hard to tell, isn't it? But you can see the actual choice you're having to make. But it should be quite easy to see that it's definitely not phenolphthalein. And the reason for that is because phenolphthalein's range sits well outside the equivalence point. However, in the third titration, the best choice would be phenolphthalein, because obviously the equivalence point favours the working pH range that phenolphthalein operates in. So it does help illustrate the care that needs to be taken when you're choosing your indicator. In the case of a weak acid, weak base titration, it's very hard to work out what indicator might be the right one to use. So although at first glance it might seem that bromothymol blue would be the one to choose, the equivalence point is it's a very narrow pH range, which will be quite hard to visually capture if you're just using an indicator in the naked eye. So to get around this problem in the laboratory, we use a pH meter. This is an electronic device that can be connected to a tablet or a computer and gives us a constant reading throughout the titration. So plotting pH against volume in a pH curve allows us to see the equivalence point on that pH curve for a weak acid, weak base titration. Another way of looking at it might be to say that the end point of the indicator in a weak acid, weak base titration is difficult to judge. So again, this is why we use pH meters to try and tell us the exact equivalence point of these types of titrations. So at this point it would be a good idea to clarify the difference between the equivalence point and the end point. So to recap, the equivalence point is the point during a titration when the volume of one solution has reacted exactly with the volume of the other. It also happens to be the point at which neutralization occurs, and if your titration is an acid-alkali titration, H plus and OH minus will be equimolar in the mixture at this particular point. An end point, by comparison, is the point in the titration where the indicator changes colour, so the end point is to do with the indicator. The solutions will have just reacted completely with each other, and the colour change will have happened. So how come different indicators work in different pH ranges? Well, as we talked about a little while ago, all indicators are essentially weak acids, and therefore they'll behave as weak acids in equilibrium, as the diagram shows. So each weak acid, and therefore each indicator, will have its own unique Ka value. It will also have its own Ka expression. And when the indicator changes colour at its endpoint, this is the pH at which the concentration of Ha, the indicator itself, is the same as the concentration of its conjugate base, A minus, or in minus, that we talked about a slide ago. Now if we apply this idea to the Ka expression, as you'd expect, you can cancel out Ha and A minus. And therefore pKa will equal pH at the endpoint of the indicator. And as you'd expect, this individual pH value will be different for each individual indicator, hence why the three indicators in the diagram work at three different pH ranges. So let's have a look at an exam question that involves using a pH curve and also involves choosing an indicator. It talks about a titration between methanoic acid and aqueous sodium hydroxide. It's obviously a weak acid strong base titration, and asks you to write a balanced equation for the reaction between methanoic acid and sodium hydroxide. So that gives us something like this. So let's move the page down and we can have a look at the pH curve and what they're asking us to do. So it says part of the pH curve for this titration is shown below. So as you'd expect, the rest of the pH curve would look something like that. And it asks you to calculate the concentration. So what you've got to do is look at the equivalence point and see what volume of sodium hydroxide was added at the equivalence point. And you can see quite clearly that it's 30 centimeters cubed. If we go back to the original part of the question, it tells you what the concentration of the methanoic acid and the volume of the methanoic acid is, so you can work out the moles of methanoic acid that were used at this equivalence point. And that gives us 3.75 times 10 to the minus 4 moles. And from the equation we know that there's a mole ratio of 1 to 1 between methanoic acid and sodium hydroxide. Let's have another look just to be sure. There you go, 1 to 1. So we can apply N over V, knowing that the moles of sodium hydroxide is the same as the moles of methanoic acid. Don't forget that 30 is in centimetres cubed, so we have to divide it by 1000 to turn it into decimeters cubed, and that gives us 0.0125 as our concentration of sodium hydroxide. So let's now have another look at the next part of the question. It asks you to calculate the pH of the aqueous sodium hydroxide, but it gives you the kW expression, or the kW value, so this means use the kW expression. So we know that kW is the concentration of hydrogen ions times the concentration of hydroxide ions. So rearranging the equation so that the concentration of H plus is the subject, you get the concentration of H plus equals 1 times 10 to the minus 14 over 0.025, which gives you 8 times 10 to the minus 13. And plugging that into the pH expression at the bottom left hand corner of the screen, this gives us a pH of 12.10, which is what you'd expect for a strong base or a strong alkali like sodium hydroxide. So let's now move over the page to the next part of the question. So this part of the question asks you to choose which indicator would be suitable and explain your choice. Now obviously we've gone past the page where we've got the pH curve, which allows you to do that. So I'm going to take a photograph of that particular pH curve and pop it on the screen for you so you can see where I'm coming from. So we've got a picture there. I'm just going to make the picture a bit bigger so you can see the actual pH value next to the equivalence point. So you can clearly see the equivalence point, so that would mean you need a working pH range of between about 5 and 9. In other words, it needs to match the vertical part of the equivalence point. So let's now go back to the question, and with that, armed with that knowledge, we can now have a think about what choice we're going to make. So the obvious choice would be metacresol purple. So we say it's because its working pH range coincides with the pH change during the equivalence point of this titration. So try at all times to be specific in your explanation so the examiner has no doubt in his or her mind as to what you're trying to say. So let's now have a look at the mark scheme to this question. We need to pull the page down to reveal it. So we got our equation, we worked out the number of moles of methanoic acid, we identified that the volume reacting at the equivalence point is 30 centimeters cubed, the volume of base reacting that is, and therefore we worked out that the concentration of sodium hydroxide was 0.0125. We wrote out the kW expression because the question was hinting at us to do that because it mentioned the value for kW. We put in the kW value and worked out what H plus concentration was, which is now highlighted, which therefore allows us to work out the pH at 12.10. We correctly chose metacresol purple, and we said that its working pH range coincides with the pH change during the equivalence point. So we got that mark as well. So hopefully this has been a fairly useful introduction to the uses of indicators and how they actually work in terms of neutralization, how they actually respond to different working pH ranges, how different acid-base combinations can actually give you different equivalence points, and how we can plot all of this on a pH curve. If you've got any queries, then please don't hesitate to go and see your teacher, or maybe come in and see one of us in a subject extension next time you're in college. But for now, thanks for your patience and thanks for sticking with this, and see you soon.